Okay, so in this video, I want to kind of try to recap an entire course in one video, but do it from the perspective um, that we've already sort of seen the nuts and bolts, and we want to talk about sort of what's really happening here. So the title here is Machine Learning, but I kind of want to put machine in quotes to sort of downplay the fact that the machine is doing the learning here and maybe sort of suggest that humans have a lot more to do with this. Okay, so, and again, this is a bit of my opinion, but machine learning sort of boils down to three things. Some data, the way we viewed machine learning, you need data to learn from. Models, which sort of tells us, maybe make some assumptions about structure within the data, or tells us sort of how to do certain things within the data. And sort of related to that is optimization. So you could think of the model as sort of expressing relationships between like response and predictors, say like the way a linear model does. And then by optimization, I mean, well, how do you actually fit that model to data? And um, I think it's important to realize that humans are sort of the ones that are um, doing these things. So I would say that data is created by domain experts. We're not letting machines sort of just collect data by themselves. Like a human is using a machine to collect data, but the humans are ultimately driving what data we're collecting. And generally, people with interest in a certain field are collecting certain data, and that's how we obtain that data. Models, I like to think, is the purview of statisticians. So obviously, we don't own models, but generally, the type of person that thinks about um, models and um, comparing models, writing down models, thinking about what the models tell us, and generally just people that come up with probabilistic models like this, statisticians are probably the most interested in that. And then optimization, or that is to say, well, you've thought up this crazy complicated model. How do you actually fit it to the data in the computer? I would sort of call those people maybe ML engineers. But I would also say that these three sort of humans that are affecting machine learning aren't sort of separated. So like you could envision someone who's sort of a domain expert slash statistician. So this would be a person that operates at the level of, well, I got some data I want to analyze because it's important to me, and I know enough about models to sort of use a statistical programming language like R and built-in packages to fit the models, but I'm not coming up with new models myself and then telling the computer how to fit them. That would be maybe someone down here, some combination of a statistician and engineer, and that would be the kind of thing that I think that more so would be called a machine learning engineer. It's someone who can both write down a new model and then instruct the computer how to fit that model. And somewhere out there is this data scientist label, which is some combination of all these things, depending on who you ask. Um, I personally think that the data scientists should sort of be most focused up here and then use models as sort of tools, but that's just my opinion. Um, but I want to stress this idea that a human is really driving what's going on here. It's not the machine. So we could ask the question, sort of, why are we even interested in machine learning? And the sort of framework that we've mostly worked in within this class is the idea that we want to predict future observations. And by future, I mean new in the sense that they were not available when we were training the model. So I'll call that train time. Okay. Um, and I want to make a note here about correlation versus causation. So correlation, that is association among variables, or just any old relationship. It doesn't have to be a specific like Pearson's correlation or anything. It could be any sort of relationship that we can learn. That's useful for making predictions. So in this graphic here, I have a scatter plot of let's suppose I went into an elementary school, grades like kindergarten, first all the way through fifth, and I measured shoe size of all of the kids and their reading ability. Right. This is not what the data would actually look like. But let's say it looks like this. This is reasonable. Um, so one thing that we could say from this graphic is that shoe size is a useful predictor of reading activity. Reading ability. That's just true. Like there's a strong correlation between these things, and that is useful for prediction. What this observational data that I had here cannot get me is causation. Causation is great to know about, but what we've done in this class does not tell us anything about causation. You would have to be much more careful about one, how you collect the data, and then two, how you analyze it. So the thing we care about in this class is the relationship between two variables. But we're not concerned with what is actually causing that relationship. In this example here, what's causing this relationship is that as you grow older, your feet get bigger, and also you get better at reading. That's not what this analysis will tell us. What this analysis tells us is that shoe size is a useful predictor of reading activity. Okay, so the task that we were doing there was a regression. And I just want you to take away that what regression really is, if we think about, well, we want to minimize these future errors, and commonly we cared about a squared error loss, what we want to do is we want to estimate the conditional mean of whatever variable we're interested in. So this picture I have here is, let's say, I guess this is X and this is Y, just in case that wasn't clear. We have some data, and here we're pretending that we know the data generating process. That is, this pink curve here is the true mean of Y given X, and that's what we would hope to estimate from some data. So hopefully, maybe if we fit k nearest neighbors to this, this is not going to be correct at all, but it would be maybe for some value of k, it would look like that. Probably not. I'm really just absolutely guessing there. But we see that while this doesn't perfectly match the true mean, we can see how we're capturing signal there, not necessarily noise. More on that, capturing the signal, not the noise, in a second. The other task that we really paid attention to was classification. And often when you talk about classification, people think, oh, you want to make classifications. I would prefer we don't think of it that way, and instead we think of it as estimating the conditional distribution of that categorical response variable Y given the features X. Now, through that, you could make classifications. So here we're suggesting that we'll make the classifications according to whichever class has the highest probability. But we've seen that we could, say, in the binary classification setting, manipulate how we do that and maybe bias our result towards one class or the other. But it's more powerful to be able to describe things this way than it is with a simple classification. But so thinking about this, the way we're doing this is with models, but in general, if we just look at this picture real fast, um, any of the models that we sort of talked about in this class, if we tried to predict if this black dot here, we would hope that it has a high probability of pink and a low probability of gray. If we tried to predict at this black X, we would hope that our model returns a high probability of gray, low probability of pink. If it was something like this, trying to predict at this black square, well, we would hope that our model is somewhat uncertain here, and we end up with a probability that's like 50-50 gray and pink. Okay. So, and then a question to maybe think about is, well, what should we do about maybe this star out here? What probability should we attach here? One way of thinking of this is that it should be, a high probability of gray and a low probability of pink. Another way of thinking about it is simply saying that, like, well, hey, that's way outside of any of the data that we saw. Maybe don't do a prediction at all, but that's something to think about. And I just want to make a quick note here. We sort of have largely ignored unsupervised learning. So in unsupervised learning, effectively either basically you don't have a response variable. You just have the variables that you have. And you try to model, say, the joint distribution of those things instead of the distribution of y conditioned on x. So we could apply certain models, like say a mixture model, to this data we have here, ignoring y as a response. We'll maybe cast that aside still, because I want to keep talking about supervised learning, because that's what the analyses we're going to do are more based on. But that's a quick way to think about this. Like, we want to model this data that we're looking at here, but without considering y as the response. Okay, so in this class, we have almost exclusively restricted ourselves to what I would call tabular data, where rows indicate observations, that is, individuals or objects that we're sort of collecting data about, and then columns represent the variables, that is, the attributes of those observations. That's what we call data. But before you sort of start modeling these things, there's a lot of questions you should ask yourself. On the observation side, you should say, how were they collected? And I think to understand what I mean by that question, thinking about how will they be collected? So what I mean is, how were they collected? That is, how did you obtain the data that you use to train and fit these models, versus how will they be collected when you go to make predictions? If they weren't collected in the same way, maybe say, some of the data was on individuals at the University of Illinois, and then you go and try to predict on, I don't know, let's say Harvard students. Perhaps your predictive model won't work too well, because you trained on a different population than you're trying to make predictions on. So keep that in mind. Should they be collected is a good question. So the example that I sort of just said there is, maybe we're doing some predictive model about University of Illinois students. Should we be doing that? Is that an ethical thing to do? But we'll need to talk about that in a variable setting a little bit more so. Another question is sort of, how should they be split? We sort of always in this class suggested like an 80% training, 20% testing split. But suppose you're in a much smaller, suppose you don't have a lot of data, and what that means is even flexible. Maybe you want to spend less of your data on testing, or in other cases, more of it on testing. It's something to think about, but we're not going to dwell on. But it is something that you, as an analyst, could control. Within the variables side of things, something you need to ask yourself is, what are the data types? Are these variables categorical or numeric, which is what we've seen here? Maybe something else if you're looking at like maybe text or something, which might get broken down into those categories. what is the response variable? If we're doing supervised learning, that's probably the most important thing. And you should ask yourself the question, like, why do we want to predict this thing? Um, Related to what I said before is what is available at test time. So obviously, we want to predict the response value in the future, but we have to also make sure that we can measure the features that are the inputs to our model. Otherwise, it won't work in the future. Um, if you're designing a system from scratch where you get to build up the data set, you have to ask yourself the question, what can we actually measure? Sometimes the variable you want to measure is expensive to measure, and maybe you have to find some cheaper proxies, but you have to weigh those things. What should you measure? So, like, this is what attributes about a person are you going to collect? I think an example that we can all sort of relate to these days is let's talk about, say, something like Proctorio is something that's on everyone's mind, right? So you could imagine that they could be running predictive models on their data, where an observation of data is, let's say, a test taken by a student, and let's say that a variable in that data set is I don't know, let's say, I mean, these variables might not be numbers and things, but like, say, a variable would be whether or not the student show their ID, or a variable could be whether or not the student looked away from the camera, and all sorts of things. And you could question every single one of those things. Is it something that they should measure and store? Sure, it might be useful for prediction, like if they want to catch later cheating, but is it something that's ethical to even store? I'm not going to sort of give an opinion on that, but it's a question that you need to ask every time you're collecting data. I have here, can you remove anything? So just because you have data available doesn't mean you even need to consider it in your model. There might be reasons for keeping variables out of even being considered in the model. And then what can you change and add? And that's sort of like, you could do any transformation to any variable and consider it a new feature. That's sort of part of the modeling procedure. And that sort of really expands the space of what an analyst can think about. And then something that we haven't dwelled on much here is, well, what if we have missing data? Yeah, that's a hard one. But you have to consider if you do, and either do some data imputation or remove it and understand the consequences of that. But so after we sort of resolve those things, what we generally do is we split up the data into a test and a train set. And our goal here is we want a good model. And again, what that means is it fits the data well and is useful. Useful here is sort of, depending on the context of the problem, fits the data well is sort of something that we attempt to sort of quantify through this test, train, split sort of thing. So within the training set, we generally cross-validate, and that's where we do this whole repeating of an estimation set and a validation set, and we repeat that. I'm going to write this down on the next slide, but that's sort of the general tuning process. And then with the test set, we sort of verify that result and calculate sort of like a generalized error. There's a generalization error, like how well will this thing work on unseen data. Sort of a little bit more specifically going through the process here. So we have some data that looks like this. So the first thing we do is we define the prediction goal. That is to say, why do we care about making predictions about this, in this case, y variable? If you can't answer that question, it's kind of odd to even go through the modeling process. The next thing you have to do is go through some of that, those questions that I talked about, but in particular, you need to define what the response is. And if it's categorical, it's classification. If not, it's regression. And think about missing data, because if you don't, you can't do it. Then we're going to talk about test train splitting the data. So we'll do something like, suppose the data was randomly shuffled in order. Well, here is the training data, and then here is the testing data. And then we estimation validation split. So again, we're sort of assuming things are shuffled. So here we have the estimation, and here we have the validation. Except if we're doing cross validation, we would repeat that a bunch of times. So those two steps here, we would repeat. I guess I skipped talking about this, which is along the way, we would have already chosen our models, possible tuning parameters, and possible sort of like variable selection things along the way. And we would be testing that procedure via cross validation to see which sort of model we choose in the end. And whichever model based on the cross validation results we determine is the one we like, we then we refit that exact model on the training data, and then we check the predictions on the test data. And when we do that, we want to keep in mind the goal of the analysis. That is, if you look at your predictions on the test data and say just calculate an RMSE, well, that's good, but you need to say, well, what does that RMSE do for me? What do these errors look like? Like, what would one of these errors look like from a business decision perspective? Like, would it ruin my company if I made an error as big as I made in this test data? Those are the kind of things we need to be asking. Okay, so another way to sort of frame this is we have this magic sort of machine learning box, and we feed it data, models, and sort of the instructions for how to do the optimization, and it spits out predictions on the other end. So what I want to say is that, again, a human decides what data to use, which also kind of drives the type of questions and sort of predictions we're going to even make. A human decides sort of what models to even consider, and then a human at one point or another wrote the optimization routines, and then out on the other side it makes predictions, but a machine can't tell you what those predictions are useful for. You have to have a human look at those predictions and tell you what, if anything, useful is going on. So another way that I like to think about this is this magic that's sort of happening that everyone thinks, oh, machine learning is super cool, is really just a computer that's following instructions. And one way to think about this is what following those instructions really amount to is memorizing the data in very specific ways. It's kind of what all machine learning algorithms do under the hood from a certain perspective. So I just want to put forward this idea that machine learning is sort of a hot topic, and it sort of sounds like this cool thing, but at its core, it's just a set of instructions applied to some data. Humans are doing all the interesting input and checking of the output. The machine is just learning a function through us setting up some instructions for it. So with that in mind, I want to just leave you with the question, why? We should always be asking the question, why are we doing this? Sometimes in classroom settings, it feels like we're fitting models because an instructor like me told you to do so. But in the real world, you should always ask yourself, why are we making this model? Like, what is the usefulness of predicting whatever quantity we're thinking about? If you can't even answer that question, you're probably just making a model for the sake of making a model. Making models should come with a reason. If not, even evaluating it seems kind of hard because you don't have a reason to do it. You don't know what those predictions can do for you. Okay, so those are a few ideas. Hopefully that'll sort of give you some thoughts about the analyses if you do them. I want to mention that this procedure that I've written down here, especially starting here, we kind of have been repeating ourselves a lot with, we keep rewriting the same code that splits the data and then we create the folds and then fit our models, and it's kind of, it seems like we could speed up that process, and that's what the next video will be about.